In today's class, we will cover a very important topic, that is what is universal language and what is universal Turing machine. Now we are going to define this universal language as L of U. That is the language which is going to get accepted by a Turing machine, which we will call as universal Turing machine, right? So we will see that how this universal Turing machine will work and how can we prove that okay, this is going to accept the strings of LU, right? Now if you remember that we have learned that how to represent the total transitions or total states and everything of a Turing machine, rather every working of a Turing machine in form of binary strings. We have learned the codes for Turing machine. There we know how to represent a total transition of a Turing machine using only the bits of zeros and ones, right? Here we will use that technique which we have learned and we can prove accordingly, right? Now here LU, the universal language, will be defined as a set of binary strings that encode in the notation of a pair, that is M comma W. If you remember, we used to represent the notation in this form, that is M stands for a Turing machine and W stands for the input alphabet or the string which this machine is going to accept, and that string will always be a combination of zeros and ones, right? So here LU is a set of strings representing a Turing machine and an input accepted by that Turing machine. Now here our job will be to show that there will be a Turing machine U. Here we will use this name U because we are going to prove this is the universal Turing machine. That's why we will use U here, right? And often this is called universal Turing machine, such that LU is equals to L of U. That means this language LU is going to accept all the languages, or this language will fall in the class of languages which my universal Turing machine accepts, right? Fine. So let us see how to move on. If we have to represent this U, that is universal Turing machine, it's the most easiest way to represent it in the form of multi-tape Turing machine. Fine. Here do not get confused in the diagram that there are several number of tapes. There are only 4 tapes. Okay, the diagram has been drawn in the book in such a fashion that first tape is the input, then there a gap they have kept just for the soothing of, means for eye soothingness, right? No, nothing else. That is not whatever say input, first tape is input, second tape is tape of M, and space between it is nothing. You can draw consecutively as well, but if you draw in this manner, so we can distinguish between the tapes. That is why there are 4 tapes total. Okay, so it is easiest way to describe U as a multi-tape Turing machine. So in this case, how the tapes will work: the transitions of M are stored initially on the first tape along with the string W. Do not get confused that we are storing the transitions of M and W. That means we are just storing in the form it is given to us, right? And then we will convert it to the form of binary strings, right? So firstly, what we are doing in the first tape, first input tape, we are going to store our transitions of M and along with that the input alphabet, right? And a second tape will be there that is used to hold the simulated tape of M using the same format as the code of M. So what we are going to do in the second tape, we are going to mimic, or we are going to simulate my first tape, but we at the same time we are going to convert it into the code for Turing machine using the technique which we have learned so far. We will use the technique to convert to to simulate the Turing tape of first tape of this Turing machine, right? So how it will be converted? That is, tape symbol of xi of M will be represented by 0 to the power I, and tape symbols will be separated by single ones. If you remember, if we had to code the total Turing machine, how we coded it? 0 to the power I 1, 0 to the power j 1, 0 to the power k, in this fashion, right? So if we have to code a tape symbol, how we did it? Whatever the suffix of my tape symbol is, that is, if x suffix I, say I is 5, then it will be represented by 5 zeros, that is 0 to the power 5. So 5 consecutive zeros will be there. And we know we used 1 as a separator between these two different tape symbols, right? Now what is the job of the third tape? The third tape of U holds a state of M with state I, Qi, represented by I zeros, right? So if you remember how we represented a state, say we had a state, namely Q1. So how we represented it? We represented it by 1, that means 1 0, right? If we had Q2, so we represented it by 2 zeros. It is Q3, we represented it by 3 zeros, and so on, right? So this was the fashion we used, right? Now the operation of U can be summarized as follows. How it is going to operate? Examine the input to make sure that the code for M is a legitimate code for some Turing machine. If not, U halts without accepting. Obviously, so if this input, whatever the input we are going to fed to this one, if it is not in the form of M, W, or it is not following the correct code for Turing machine technique, that is binary representation, you cannot accept anything, means you cannot work in that fashion. It has not been trained in that way, right? So it is going to get halt and it will not accept a string. So the job is done. And since invalid codes are not going to get accepted by the Turing machine, right? So it will halt there. No issue. Now if if the code is in the correct fashion, so how we are going to start? Now initially the second tape, we are initializing the second tape to contain the input W in its encoded form. See, the second tape is doing what? It is containing the W, as we have already told that second tape is going to hold the binary representation of the first tape. So first tape content will be what? The input string only, the binary means the input which it is going to process. So the encoded version of that W we are going to fed to the second tape, right? So that is how we are going to represent it. For each 0 of W, place 1 0 on the second tape, and for each 1 of the W, place 1 0 there. So if you remember, if my first symbol, that is if it was x0, right, means if it is 0, so how we are going to represent it? We will write it as 1 0 and a 1 beforehand. If you remember the binary representation, we used to represent it with 1 followed by W, right? 1 followed by W. So if 1 0 is there, so it will be 1 0, right, since only 0 is there. Now if you remember, the representation for 1 was what? X1, right? For 0 it was, sorry, for 0 it was X1, for 1 it was X2, and for blank it was X3, right? So if you have forgotten, please follow the code for Turing machine lecture. There we have introduced this fashion. If we have to represent 0, the tape symbol 0, we used X1. If we have to represent tape symbol 1, we used to represent it by X2, and for blank it is X3. So since the binary representation is of the form 1 followed by W, right? So for 0, what is the representation? X1. So how many zeros will be there? Only 1 0, right? That's why 1 0 for 0. For 1, what is the representation? X2. So how many zeros should be there? 2 zeros, right? So it will be 100. If it's a blank, what is the representation? X3. That means how many zeros will be there? 3 zeros. That's why 100. But here it is not going to store any blank before, and because whenever there is a continuous input streams, that is W, there is no question of keeping blank. But so this 100 is not going to use. But means if all say all means if in my Turing machine afterwards it finds that okay, it has to replace something by blank, so it will replace that by 100. That is, but for initially we are not having any blank in between, that's why this 100 will not be used. We will be using only 10 and 100 for now. Okay, fine. Now what we will do, we'll place 0, that is the start state of M, on the third tape and move the head of the U's second tape to the first simulated cell. Why so? Why we are placing 0 on as a start state of M on the third tape? Because if we assume that it starts with the initial state, that is Q0, so what value we are going to store there? Only 0, right? So the initial state means 0 only. That's why in the third tape, if you look at the diagram, it has marked with state of M, so it will start with 0 only, right? And move the head of the U second tape to the first simulated cell. Why we are moving it to the first simulated cell? Because it is going to start processing, so the processing starts from the left hand side. That's why we have to move the control unit or move the pointer towards the first simulated cell, so it can start processing there. Now if we have to simulate a move, if you remember, if we have to simulate a move, that means we have to follow what are the transition rules given here, right? Say one transition rule is given like delta q0 comma 0 is equals to q1 comma say 1 comma right. So how we are going to simulate it? We are going to simulate it in this fashion. My first thing is q0, okay, so that will be raised to the power of first 0 to the power I. That means if the code is 0 to the power I1, 0 to the power j, 0 to the power k, in this fashion it is there. So first q0 means the suffix of q will be raised to the first zero's power, that is I, right? I will be that value. Then if we have 0 there, the initial tape symbol, so we have to represent it by what? 0 stands for x1, so it will be x1. Okay, so x1 will be what? That is the suffix is what? 1. So j's value will be 1, right? So in this fashion we have learned already how to code it, and again then it will move to the right hand output, so it will replace accordingly and first code will be generated. Fine. Now see that here what is happening, such that here 0 to the power I is a state on the tape 3, right? Why? Because in the tape 3 we have initiated the starting state. So here in the left hand side of the transition function, it will definitely start with the starting state, delta of start initial state comma tape symbol. So that's why the 0 I will stand for the first symbol, first tape symbol of the tape 3, right? And that begins at the position on tape 2 scanned by you, right? So again how it is going to process this 0 to the power j, it will look at the tape second tape, and it is second tape is storing what? Second tape is storing my w, that is input string in form of binary strings. So first whatever the cell it is pointing at, means which cell it is currently that is leftmost cell, that is the 0 to the power j, right? And for the rest 0 to the power k is for the next state, k stands for the next state, and l for the output symbol, and m for the movement. D1 stands for left movement and D2 stands for right movement. We have learnt in the coding part. Okay, now how it's going to change the contents of the tape 3 to 0 to the power k. Why it will change it to 0 to the power k? Because the next state is holding at 0 to the power k, whatever the value of k is. So it is nothing but it is depicting which state it has to move to. That's why the contents of tape 3 is going to get changed to 0 to the power k, because the next iteration we will consider this 0 to the power k as my previous state, or the state from which we are going to process next, right? So in this fashion it will keep on moving. You can easily understand, right? Now next what we will do, we will replace 0 to the power j on the tape 2 by 0 to the power l, because we have come to the next state now, and we have seen what my 0 to the power j has been converted. It has been converted to what? 0 to the power l. So l's value is now the next tape symbol, right? So here it will be stored in the step 2, because next we are going to use that tape symbol. Okay, use that value to work again in the following the same fashion. Now one more technique is there. If more or less space is needed, use the scratch tape and shifting over technique to manage the spacing. Now here we are not going to cover this shifting over technique because it is not included in your syllabus. Still, if you want to learn what is shifting over technique, you can follow the ebook, that is Hopcroft book, which I have shared with you. You will find it in, I think, in chapter 8 it is there. So you can find it, the shifting over technique, how it is going to work on. So for now, just we will concentrate on this one. So if more space or less space are required, then this scratch tape will be used. It is nothing but a extra memory space is given there, where we can use a swapping process or shifting. Will give something, we will do like this. Okay, so if you want to learn the details, you can follow there. Okay. Next, move the head on tape 2 to the position of the next one to the left or right respectively, depending on whether m equals to 1 or m equals to 2, right? So we know that D1 stands for left movement and D2 stands for right movement. So whatever the suffix of D is, we used to raise that to the power of m. That's why depending on m's value, whether m is 1, we will move left. If m's value is 2, we will move right. Thus what is happening here? Thus u simulates the move of m to the left or to the right. So you can simulate the movement as well. You can see here what m you can do. You can process all the input, you can transit from one state to another. At the same time, you can even move from left to right. So it is working similar to the Turing machine, right? No issue with it. So what we have seen, that if m has no transition that matches the simulated state and the tape symbol, then in 4 no transition will be found, right? So you can follow the points whichever what is the fourth number point. So if it has no transition, if it does not matches any simulation, so it is not going to do any transition, right? So m will halt there, right? M will halt there and will be non-functional there, and if not, then it will work in the manner which we have explained so far. Now if m enters its accepting state, then u accepts. So if m enters its accepting state by following this fashion repeatedly, that means u is again going to accept the same string which m has accepted, right? So what u is doing, u is simulating m on w, means u is simulating my Turing machine m on the input symbol w, and it accepts the coded pair m comma w. If this condition satisfied, that if m accepts w, then u is going to accept w as well, right? So you can see that when we are going to this universal Turing machine approach, again we have successfully simulated all the working of a Turing machine m following the binary coded fashion, right? So this Turing machine works well. Now again I have left one more exercise for you. if you want to go to a proof that my Turing machine, that this universal Turing machine, it forms in which class, it is recursively enumerable or recursive. Okay, so you may follow the ebook, that is Hopcroft book. There you will find a proof, it is given. Still it is not so important, but if you want to learn, you may go there and learn it. Okay, and this much for today. In the next class we are going to see some undecidable problems about Turing machine. Thank you.